As we now move on to our next topic, it's interesting to take a look at what the experiments actually show us about the energy of hydrogen atoms. Now, for this, the typical experiment we would do is we would here, let me move the axis over here for you a little bit, is we would want to then measure the energy of a series of hydrogen atoms. And to record our results and to record down what the probability we find associated with these various different energies. And there are two cases I'd like for us to consider for this. One is when we have some very carefully prepared systems. By carefully prepared, we've done everything we can to ensure that our hydrogen atoms have achieved their lowest possible energy states. We've isolated the atoms, we've given them a long time to radiate away any excess energy, and then we go ahead and measure their energies. And when we look at this probability distribution, we find very nicely that in fact this energy that we've calculated, 13.65 electron volts, figures in very prominently in our results. But we find something surprising. If you think about our past analysis, we can go back to, maybe, actually, let's go right to the very beginning, right? The energy for each system should be p squared, right, with constants minus basically this 1 over r potential. And notice that we're expecting that there's going to be a range of values for p. So this kinetic energy term should be fluctuating around quite a lot. It's some kind of random number. It's got some sort of average value, but it's still, on individual instances, I can get quite a range of values. Likewise, the position of the particle, we said, it can't be completely localized anywhere. That would be a huge confinement energy. But rather, we get a range of positions, and therefore we're getting a range of potential energies. So you might expect then that when we go in and measure the energy, we have these fluctuating kinetic energies and these fluctuating potential energies. So kind of what we would expect is a range of energy values that tend to be centered on this minimum average value that we've computed, but we've only really estimated the average value. And you would expect maybe some kind of distribution here. But that's not what you find. What you find, in fact, is that all of your energy measurements are very sharply peaked. The only width to this peak really just comes from experimental measurement errors. You essentially get all of your hydrogen atoms come in with exactly the same energy. And that's a little bit mysterious. What that's telling you is there must be some strong correlations so that you always get this one constant value. In particular, what must be happening is that whenever the kinetic energy is a bit high due to a large momentum, you must be in a situation where the position was very small so that their sum can stay constant. What that means when you have two random variables where one, whenever it gets big, the other one gets small, or when the first one is small and then the second one has to get big again, that's a situation known as correlation. There must be a very strong correlation in this case between the position and the momentum. And this is not something that we necessarily would expect from our simple Heisenberg uncertainty principle. So that's why we are thinking, there should be a strong here, let me write it out a little more clearly. That's why there seems to be some extra piece of physics that we're missing right now. And this Heisenberg uncertainty principle just isn't enough really to explain these strong correlations and the fact that I get this just one particular energy value. And the situation gets even a little more mysterious if you look at some less carefully prepared systems. Okay, so you might imagine, okay, something special is happening when everybody's settled down into the same state. But now, what if I don't wait? What if I'm not as patient as I should be? And I allow the systems to not be fully relaxed? You might ask yourself, okay, maybe now I'm going to see some kind of spread in my results. And you do in a way, but again, it's a surprising way. So here's my special 13.65 electron volts. And even when you don't have them all in their lowest energy state, and you go and do measurements, what you find is this. You find again a very sharp peak, maybe not as high, but a very sharp peak around 13.65. And then you find another very sharp peak at some higher value, and then another one, and they actually end up coming closer and closer together. And what you get is this series of discrete peaks centered around very discrete values of the energy. So the energies measured experimentally always end up are always certain special, and it's very important here that these are discrete, right? There's no continuum. You never measure energy values in between. They are certain special discrete values. And this general concept is actually called a quantization, right? They're discrete. There's something countable. This is known as the quantization of energy states. And of course, that's where quantum mechanics actually gets its name. Now, to understand this, we are going to need some further principle beyond Heisenberg in order to be able to explain and predict this type of phenomena. And that is going to be our next topic after we explore in a little bit more depth the direct experimental evidence for the existence of these discrete levels, because that evidence is going to give us some very strong clues actually as to the origin of this interesting phenomenon.